class will be dedicated to the numerical differentiation. This week, I think, according to my knowledge, and this is my actually suggestion to you, today's class just a theoretical class, okay? And then we will also see today, next week, we will try to learn here the numerical integration, and you will see next week on the MATLAB cases, okay? This will be the application for you. Okay, everyone. So the main important thing here I wish to say, actually, the thing here is that for solving actually we are just using here the baby steps, okay, to go to solving the numerical solution of the differential equations. This is the thing. Actually, this is our purpose to go there. This is our purpose. So as a starting point, we are trying to understand the numerical differentiation and the numerical integration. Why? Because the numerical integration will be helpful for solving the initial value problems, and the numerical differentiation will be helpful for solving the boundary value problems. So, as you know, numerical methods is an approximation theory. It's an approximation methods. It gives us the approximations to use all the knowledge in the mathematics that we have used in previous. So let us see here the numerical differentiation subject. Okay, everything for the numerical approximations, guys, based on Taylor approximation, Taylor series. Why? Because all the functions have Taylor series formalization, like a polynomial version, to represent themselves. Okay, so it means that by using a series representation, I can write down any function which is analytic. The analytic as a word, it means that it has infinitely many derivatives, and also all the derivatives are continuous. This is it means that this is corresponding, it covers the analytical function. Okay, so here is a reminder for you. This is the Taylor series, actually, you can see that. Let me take my pencil. It's so important because this should be better for our understanding. Okay, so when we are considering the Taylor series, I can open here the f of x plus h, f of x plus h times f prime x plus h squared times f double prime x. We are considering them. Oops, not responding. My computer is broken now, I think. It's locked. Could you hear me, everyone? Okay, so we have seen here the approximation by considering here fx plus h. So when you are considering this function about the Taylor series, you are considering this is your center point. I mean here, the Taylor series expansion around x. We are calling this type expression by considering around x. Why it is important? Because in the approximation theory, for the consistency, we need to be sure our approximated value or our approximated scheme will be appropriate for the exact solution. For this reason, we are considering here an exact solution, and I'm using just first two terms, three terms, a fifth terms we are taken from the exact solution by considering like the approximation. Okay, this is the thing. So as a general formalization, this is the closed version. This is the closed version of the Taylor series. Is considered as the infinitely many summation here, f to the power n. This n with the parentheses denotes us what? The derivative, and derivative of n, f here, x n factorial h to the power n. So by using this reminder, okay, for us, we will understand, or we will see what we will get at the end. Okay, so let us see here the construction of difference formulas. So guys, one more time, let me emphasize one more time why they are so important for engineering. So in the engineering, generally we can define our phenomena, okay, by using the mathematical language. So these models corresponding to the differential equations, okay, generally you are getting a differential equations. Of course, the interpolation is another class which is so important, but it is a little bit different from these concepts. Don't forget, it is also another important class for you, but it's a little bit different from that one, because in the interpolation you have an experiment and you are discussing the experiment, how can we fit this curve, okay, fit the data. Now you are modeling your physical phenomena by using some physical laws, okay, and after using them, using the mathematical language to determine here the model itself, and after creating it, it is returning to the differential equations. So two possibilities for you. First one, initial value problem, it can be, or it can be also boundary value problem. Okay, so for solving these types problems, we have two different ways, two different strategies. The first one, using the boundary value problem, will be solved by using the numerical differentiation, whereas for the initial value problem we have a lot of methods for solving them, but the thing is passes through the numerical integration. Okay, so for this reason, today and next week we will talk about numerical differentiation and integration. So the construction of a difference formula here, the difference equation, from now on you will see what I mean. In the continuous space we have the differential equations, okay, but we cannot solve all the differential equations directly, like you did in the when you took the class which is calling differential equations in math 205 I'm saying here. So the differential equation, in also therein you also use the power series solution, for instance, but the power series, even though you can solve by the power series, you cannot imagine here infinitely many series summation, right? So this is turning to do, okay, I need to use here some different approximations. What about them? We are considering here the difference expressions, okay? So to obtain here the difference formula, by using this difference formula, we are getting here second order, third order, fourth order derivative approximation now. So we will continue with an exercise. It could be better for your understanding. Because of this, I'm choosing here starting with an exercise. Look at here, guys. Consider the given scheme. F prime xj will be equal to alpha f of xj plus 1 beta f of xj plus order of, from now on you are familiar to see this notation. It is a notation which is calling big O. We are saying in mathematics like the big O. Okay, this is called big O. Delta x to the power gamma. Describe the values of alpha, beta, and gamma respectively. Okay, now from now on, guys, we will discuss what does it mean as xj. Okay, so here is you are having a streak. Here we are getting here a expression starting with x0 and ending with xn. Here is I also sketch it to which is depicted in this figure here. So x0 starting with and up to getting xn. So when you are considering here your increments, for the sake of clarity, we just using here the understanding easily, I mean, we are using here the uniform increment all the time. We are saying, for instance, xn, how can I find out delta x? It is obtained by xn minus x0 divided by how many intervals do we have here? N intervals. So it should be n. It is turning to delta x. So for the easy calculation, we generally, as a mathematician, as an applied scientist, we generally assume the increments are uniform, equally divided, okay? So from now on, I'm using x0 will be, for instance, by using increasing one step, which is delta x going delta x to the future means that x1. One more time, x1 go delta x increment, delta x steps you are going to means that x2. So it is observed as, for instance, as a general representation, I can write xj will become what? X0 plus j times delta x. This is my actually the problem. Okay, when you are writing here xj plus 1, it means that this is turning to xj, adding here one more delta x. So this represents us another node, okay, going to the other node here. So as you know, they are calling as nodes, or instead of this, you can also note that as nodes, okay? They are calling nodes or nodes. So we have discussed in previous. For this reason, I'm writing here xj plus delta x. Okay, when you are writing here your function, the Taylor series around xj, look at here, I fixed my xj, okay, and this is like my increment as I wrote here, like h is here is what? Delta x. Now we will write down here delta x, f derivative xj, delta x squared divided by 2 factorial, second derivative xj, and so on. Now guys, going to the previous one, look at here. In my question, this is the thing, please focus on what I'm saying here. In this process, we have two sides of the equation, right? The first side is the left side and the second side is the right side for us. In the left side, on the left side, I'm seeing here the first derivative. This is my purpose. I want to get here first derivative, just first derivative at xj node, okay? On the right side, we will use two representation, which is fxy, and f of xj plus 1, which means that f of xj plus delta x version. So, and also order representation. We will discuss order representation later in our calculations, okay? So, but I need to write down here f of xj plus 1 will be written, but on the right side what we see, alpha times f of xj plus 1 and beta times f of xj. So I wrote it, there is no more explanation and expansion of the series around xj because actually this is plus 0. When you are writing instead of delta x 0, it is nothing for you. So totally, b f of xj will be similar to same with itself, okay? So by writing here, because of the right side of the expression, as you can see here, the question states what I am doing, guys. So alpha f of xj plus 1 and beta f of xj, as here, I'm adding them, okay? Term by term, don't forget. Here is f of xj, so I have here the coefficient alpha and beta. And continue. There is no more first derivative, so alpha times delta x. And alpha times delta squared x divided by 2 factorial, something like that. So after rearranging them, you want to get what? You are trying to obtain this summation will give me here totally, this summation will return me f derivative xj. I wish to obtain it, okay? This is my objective. So when you are considering them, by matching left side and the right side together, by matching them, using the equalities, guys. On the left side, what I see here, alpha and beta is the coefficient of f of xj, but on the left side, I don't have any f of xj. So it means that the summation should be give me 0. On the left side, I'm having 1 times f prime xj, whereas on the right side, we are having alpha times delta x. So it means that this should be 1. Okay, up to here, do you have any question? Everyone, I'm asking to you. Do you have any question? Everyone, are you there? Are you there? Is everything clear? Yeah, okay. The others? Are you sleeping? You just write yes, y or just y. It's okay. Okay, then I will continue. If you are replying me yes, so there is no more problem. Okay, so let us continue with our calculation. Okay, alpha and beta. Guys, one more thing in the analysis. We are an applied scientists, okay? So we need to be sure about the mathematics. What I mean, you have here, how many unknowns do we have? Alpha and beta. So two unknowns. So for solving such system, such two unknowns variables here, how many equations do we need here? How many equations? Yeah, yes. Now I'm adding here extra, I'm adding to you extra questions, like the video question. How many equations do we have to solve this expression, two unknowns? How many equations do you have? I wrote actually. Yes, two equations. So two equations with two unknowns will matching to each other. It means that we can get unique solution by the linear algebra, as you know. So, okay. So we are considering then, I have known that from now on, two equations will be enough to solve such this system. For this reason, look at here. The first equation, alpha plus beta will be 0, and alpha times delta x is 1, they are enough to solve them. Okay, alpha plus beta is 0, alpha times delta x is 1. So by considering these equations, I'm just clearizing here my alpha and beta to define here my description of the parameters. Alpha is here is what? 1 over delta x. What about beta? Beta, by substituting in the previous one, the beta corresponding to what? Minus 1 over delta x. So here the answer will return to you like the, let me write here. After writing this expression into, okay guys, first of all, from here we are substituting by considering here alpha plus beta, which is giving you 0. This part is 0 now. And you have known that by the assumption it was 1, and then now it is turning to what about your next term? Because you have observed that alpha is 1 over delta x, by substituting it into the equation, you have observed that this is your scheme. Okay? So, guys, now we are trying to understand what does big O mean. So when I'm writing here, f prime is equal to f prime xj plus delta x divided by 2 factorial and divided by 3 factorial by the calculation, just doing the calculation here. So, okay, this is the thing again in the limit process. So we are using in numerical approximations, in numerical methods, we are using all the knowledge in previous calculus 1, calculus 2, differential equations and so on, linear algebra mainly. So you need to be understand about this one. Okay, everyone, when you are calling a big interval which is starting with x0 and going to xn, you have divided into parts, right? x1, x2, and so on. And we are saying all the increments from xj plus 1 minus xj will give me delta x. Okay, what can I say about this delta x? The delta x is actually because of the whole domain is divided into n subdivisions. This is almost generally, not generally, all the time actually, we know that this delta x is less than 1 all the time. It is greater than 0, less than 1. So it means that when delta x approach to 0, we can say that the remaining terms, which is starting with delta x divided by 2 factorial, delta square divided by 3 factorial, so it represents us actually, guys, that delta x goes to 0. This one is the biggest term. This is our biggest one. Okay, this is the big one. So the big one means that by comparing the remaining terms, for instance, if you cannot understand it directly, for instance, I can give you here, I'm taking delta x like 0.5. So by comparing, is delta x bigger than delta x squared or vice versa is true? Which one is correct for you? So you know that delta x is bigger than delta x squared because it is 0.25, but delta x 0.5. So this one is bigger, right? Means that when you are comparing the remaining terms, term by term, this is your bigger one. For this reason, we can say that my biggest term, which is our first term generally, covers here my error here. This is your error, and from now on we will write down the remaining, all the remaining part by representing using the first term as the remaining part. Okay, so it means that here we are calling from now on order of delta x. So the order of delta x here, we can rewrite finally f prime will be written. Okay guys, I'm going to the back. The back means that the question actually, okay? Look at here. I'm going to the question again. And I have described from now on, alpha is 1 over delta x, beta is minus 1 over delta x, and plus big O and delta x to the power something. So the gamma is also represented, actually described by using 1. So here is the power is saying 1. This is an important number because this number denotes you here the order of the approximation. So I mean here guys, from now on, you need to understand what does big O mean. If I am using addition big O, by the addition, look at here, I'm using equality because it is equal, because this is coming from the Taylor series. But if I don't use here the big O notation, if you don't write it, you should write down as the approximation, because you just approximate your first derivative by considering this scheme. So how does it help us here? It means that for the derivative, look at here, for the derivative approximation, I just define using my components, I just define the derivative by approximating the derivative by using my entries, okay? So this is the thing that we need to do in this today's class. So, okay guys, at that time, I should give a break because of the, I'm taking here the video record. For this reason, I should give a break at that moment, okay?